They will be looking at the lateral earth pressure theories. Now we've looked at what retaining walls are and what they are used for. Now we know that when we have a retaining wall in a way impounding soil or preventing soil from moving, let's say at this side of infrastructure, in order to maintain its stability. And so we know that the soil is going to act a form of pressure, and this pressure or stress that the soil is going to subject the retaining wall to is what we call the lateral earth pressure. And in order to find this lateral earth pressure, we are going to base it on some theories. So the first theory is that the lateral pressure from the material that is retained acts on the wall and try to move it from its position. So just as I indicated that the soil here or the rock here would in a way um, subject the retaining wall to a form of pressure, that is a lateral form of pressure that will in turn either cause it to move either by translation, so by translation or by rotation. So these are the movement forms. Now in any of these things, when these things happen, then eventually there's going to be failure because we know that the retaining wall is supposed to prevent the movement of this soil. Do you get it? And so if the soil is able to cause the retaining wall to move either by translation, so translation, we are looking at the whole retaining wall moving, the whole retaining wall moving, or by rotation, that is causing it to bend. Then we also know that the lateral pressure try to move the wall laterally by translation or rotate it about the base, just as we indicated. Now, in the design of this um, retaining walls, the wall should be designed to withstand the lateral earth pressures. Now, knowledge of earth pressure theory is needed to properly construct and design the earth retaining structures. So here we are going to look at theories, three major theories. That is the three earth pressure theories, although they are more, we are going to look at the three. That is the Rankine's earth pressure theory. Then we'll look at Coulomb's Coulomb's earth pressure theory. Then we also look at the last one, that is a log spiral earth pressure theory. Now, now, um, we know that if we have a soil layer, now we know that if we have a soil layer and we take an infinite section of this soil layer, let's say this portion of the soil layer, it's easy for us to determine the effective geostatic stress, that is the vertical stress that is acting on this soil layer. If let's say this whole thing is a soil, but it's very difficult for us to find the lateral forces acting on the soil. The lateral force, let me see this in this direction. So let's call it the effective horizontal force. It's very difficult. Do you get it? So just as we said, we need to understand these three theories, and these three theories will help us to find the lateral earth pressure. So this theory, I'm going to work on based on this theory. Do you get it? Now, in order for us to come here, that is just three major theory, just as I indicated here, that if we have, let's say, a soil layer, we have a soil layer and um we take a section of that soil layer, let's say this section, there's going to be a horizontal force acting on it, horizontal stress acting on that is the geostatic stress, effective geostatic stress. Then there's going to be the lateral forces, that is the horizontal force. Now it's very easy to find this, how do we call it, geostatic stress by the formula gamma H. That is the unit weight of the soil and the depth at which we are considering. But it's very difficult to find that of the horizontal. And so we introduce what we call the earth pressure coefficient. So we are going to look at the earth pressure coefficient and what it's all about. All right, so we are looking at the earth pressure coefficient. Now, just as I indicated that determining lateral earth pressure is not an easy thing to do as compared to determine the geostatic or effective geostatic stresses. So therefore, earth pressure coefficient is employed to find or determine the lateral. So if we have a soil layer here, I take an infinite portion of that soil layer. Let's say from here to here is a certain Z. You get it? Now, in this case, it's easy for us to find the the effective geostatic stress on this section. And so we know that the effective geostatic stress is going to be gamma H. In this case, our H is what Z. And so I can say that the stress is this, right? And I indicated that it will be very difficult for us to know this. So we introduce what we call the earth pressure coefficient, which is the key. And the earth pressure coefficient is simply the ratio of the horizontal, this guy, the lateral forces, which is also called the horizontal stress, over the vertical stress. So that is what the earth pressure coefficient is. So in simple terms, we are looking at the horizontal stress, horizontal or the lateral stresses divided by the vertical, or you can also call the geostatic stresses. And that is equal to our key. And so if we know our key, we can easily find our lateral stresses by using this equation or making the lateral stress the subject. So if you look at this diagram, so we have this AB to be a retaining wall. We have this to be the ground surface. Then we have this to be our infinite soil unit. You get it? Now from the surface to this point is Z. And so if I want to find the vertical stress on this unit, it's simply gamma gamma Z, assuming the soil has a unit weight of, let's say, has a unit weight gamma represented by gamma. And so in that case, my K is going to be the lateral stress divided by the vertical stress. And the lateral stress is equal to K, the vertical stress. But we also know that the vertical stress is what? Gamma what? Z. So this equation is also what? Important. Let's take note of that. Now, we have three major types of the earth pressure coefficient. We have three major types of the earth pressure coefficient, which we'll discuss in the next video. Now, the three major types of earth pressure coefficient depends on the movement of the retaining wall. So if the retaining wall is not going to move, we are going to have a certain earth pressure coefficient. If the retaining wall moves into the soil or the backfill that we are retaining, it's also going to have a certain earth pressure coefficient. If it moves away from the backfill, it's also we are going to have a certain earth pressure coefficient. So we are going to look at the three major types of earth pressure coefficient. All right, so we are looking at the types of earth pressure coefficient. So if you will know. Now, I said that the type of earth pressure coefficient depends on depends on the movement or position of the retaining wall. Now we have three types. Three types. So the first one is the at rest earth pressure coefficient. The second one is active earth pressure coefficient. The third one is passive earth pressure coefficient. Now we are going to take each of them one by one, but a brief story about it. A brief story about so something brief about them. So for the active, the retaining wall is static. The retaining wall is static. Just as the name implies, at rest there is no movement, so no movement. Now for the active, the retaining wall moves away from the backfill or the soil. Then for the passive, the retaining wall moves into moves into the backfill or the soil. So we are going to talk about this. Now you should know that for the at rest pressure coefficient, it to be used, that is K naught, to be used when the retaining wall is static, there is no movement. Then the active, that is Ka, when the retaining wall is moving away from the backfill or the soil. Then for the passive, that is the Kp, when the retaining wall moves. Now remember the reason why we are looking for these key, the pressure coefficients. We are looking for them because we want to find our lateral stress, because we indicated that it's very difficult in finding lateral stresses as compared to the geostatic stress, as compared to this guy. You get it? Huh. You remember this equation? Remember this equation. So in order to find our lateral stress, we need our earth pressure coefficient, and we also need our geostatic stress. And we are saying that the earth pressure coefficient that we will need, we have three types: K naught, Ka, and Kp. And each one of them is used based on the movement of the retaining wall. All right, so the first one we'll look at is the earth at rest earth pressure coefficient. So at rest, just as the name indicates, the wall is designed in such a way that it does not move. So an we are looking at an undisturbed or unrestrained soil. Do you get it? Means that there is no movement. The retaining wall is intact here. Do you get it? And so we say that the soil mass is in a state of static equilibrium. So because there is no movement, if this is the ground surface, then we take a certain soil unit here. The distance from here to here is z. Let's say the height of the retaining wall is h. Now there's going to be the vertical stress obviously acting on it, then the horizontal stress also acting on it. Now, because there is no movement, we say that the soil mass in a state of equilibrium. Then we are also saying that the earth pressure coefficient is referred to as at rest. So here, our key note is what? At rest earth pressure, at rest earth pressure coefficient. And so in this case, let's take the soil mass to be gamma, right? And so our geostatic stress in this case is going to be gamma what? Gamma Z, right? And so our K naught is going to be what? Gamma prime H. That is the lateral stress over gamma prime naught. So this key in condition where the retaining wall is static, then our K naught is what? The at rest earth pressure coefficient. And that at rest earth pressure coefficient would help us in finding our lateral stress. Now, how then do we find our K naught? Because in questions, they are going to give us parameters to find our geostatic stresses. Do you get it? And we also need to find our at rest earth pressure coefficient. How then do we find this parameter? So there are three formulas based on research by individuals. So depending on the parameters available, these formulas will be used in calculating our at rest earth pressure coefficient. So the three formulas that we are talking about. So for a loose coarse grain soil, the formula for finding K naught is equal to 1 minus sine phi. And this was by Jackie in 1944. Now phi is the angle of friction. It's a shear parameter. So when you have your you have this your shear, so we have shear force here, the normal stress here. So this shear stress diagram, and you have your failure envelope. So the angle of friction is the angle that the failure envelope makes with the normal stress axis. So this axis, again, that is your angle of friction. So for loose coarse grain soil, this is how we find the at rest earth pressure coefficient. And the second one is the dense coarse grain soil. So dense coarse grain soil, we can find our at rest earth pressure coefficient by the formula 1 minus sine phi plus gamma d over gamma d minimum minus 1 or multiplying 5.5. That is this expression multiplying 5.5. Now gamma d is a dry unit weight of the soil, and gamma d minimum is the minimum dry unit weight of the soil. Then the general, we have the general. Now this formula by Fang and Sherif in the year 1984. Then the third one, that is the general one. We have K naught is equal to 1 minus sine phi multiplying the OCR to the power sine phi. Now the OCR is the over consolidation ratio. That's our OCR. So depending on the parameters given, so for instance, if the question gives you the parameter of angle of friction, then I think that the Jackie equation will go for it. If it gives you all these parameters, then you go by Fang and Sherif one. If there is OCR, then you are going to go by this one. So yeah, basically this is how you can find K naught, and you should know that K naught will be used if the condition of the retaining wall is static. That is when there is what? Static the soil mass is in static equilibrium. All right. So we'll end here. The next thing that we'll look at variation of earth. We'll look at variation of at rest earth pressure. We'll look at in the presence of water and in the absence of water. Then we'll look at some few examples. Then it will be good to go.